Imagine holding a crystal so small it's made of just a few thousand atoms. Now, what if I told you that by simply changing the size of that tiny crystal, you could change its color, make it a little smaller, and it glows brilliant blue, a little bigger, and it shines a fiery red. This isn't science fiction. This is the incredible reality of quantum dots, and they are quietly powering a revolution that's reshaping everything from the TV in your living room to the future of cancer treatment and clean energy. Welcome to G Fun Facts Online, where today we're diving into the dawn of the nanoscale revolution. So what is the magic behind these tiny, color-shifting crystals? It all comes down to a wonderfully weird phenomenon called the quantum confinement effect. In a normal-sized piece of material, like a silicon chip, electrons have plenty of room to roam, and their energy exists in broad, continuous bands. But when you shrink that material down to just a few nanometers in diameter, we're talking smaller than a virus, the rules change. The space becomes so small that the electrons are trapped or confined. Think of it like a particle in a box. In this nanoscale box, the electrons' energy levels are no longer continuous. They become distinct, separated steps, much like the rungs on a ladder. The size of the box, or the quantum dot, determines the spacing of these rungs. A smaller dot creates a tighter box, which forces the energy levels further apart. Now, here's where the color comes in. When you energize a quantum dot, say with UV light, an electron gets kicked up to a higher energy level, but it can't stay there. It quickly falls back down to its original state, and as it does, it releases that extra energy as a single particle of light, a photon. The color of that photon depends entirely on how far the electron fell. In smaller quantum dots, the energy gap is large, so the electron takes a big leap down, releasing a high-energy photon, which we see as blue or green light. In larger quantum dots, the energy gap is smaller. The electron takes a shorter fall, releasing a lower energy photon, which we see as orange or red light. This direct link between size and color is what makes quantum dots so revolutionary. You can take a single base material, like cadmium selenide, and by simply cooking up batches of different sizes, you can make it glow in any color of the rainbow with incredible purity and brightness. The story of these artificial atoms is a fascinating journey of discovery that recently earned its pioneers the 2023 Nobel Prize in Chemistry. The first hints appeared in the early 1980s. Russian physicist Alexei Ekimov noticed that glass doped with copper chloride changed color depending on the size of the nanocrystals inside. Around the same time, Louis Bruce at Bell Labs in the US observed the same effect in liquid suspensions of nanocrystals. But the real breakthrough came in 1993, when a team at MIT, led by Mungi Bawendi, perfected a method to create high-quality quantum dots with precise control over their size. This hot injection method unlocked the door for mass production and all the applications we see today. So how are they made? The most common method is a bottom-up approach called colloidal synthesis. Think of it like making rock candy, but on a nano level. Scientists dissolve precursor chemicals in a solvent and then heat it up. They then rapidly inject another chemical, which triggers a burst of tiny seed crystals to form all at once. By carefully controlling the temperature and how long these seeds are allowed to grow, they can produce a batch of quantum dots that are all almost exactly the same size. This process gives us the precise color control we need. There are also top-down methods, where you start with a larger block of material and essentially carve out the quantum dots. But for making the large quantities needed for TVs or solar panels, the bottom-up chemical synthesis is king. This precise control over light has unleashed a torrent of applications. The most visible one is probably sitting in your local electronics store, QLED TVs. The Q stands for quantum dot. In most current QLEDs, a sheet filled with red and green quantum dots is placed in front of a blue LED backlight. The blue light energizes the dots. The smaller dots emit pure green, and the larger dots emit pure red. This pure red, green, and the original blue light combine to create the images on your screen. Because the colors are generated directly by the dots, they are incredibly vibrant and pure, allowing for a much wider range of colors and brighter images than traditional LCDs. The next step is even more exciting. True QLED displays where the quantum dots aren't just filters, but the light source itself. An electric current would be applied directly to the dots, making them light up. This would create displays that are even thinner, more efficient, and potentially flexible. But it's not just about better entertainment. Quantum dots could be key to a cleaner energy future. A standard silicon solar cell has a theoretical maximum efficiency of about 33%, known as the Shockley-Queisser limit. This is because silicon can only efficiently absorb a specific slice of the sun's light spectrum. Quantum dots can blow past this limit. By using a mix of different sized dots, a solar panel could be tuned to absorb the entire solar spectrum, from visible light all the way to infrared. Even more amazingly, quantum dots can perform a trick called multiple exciton generation, or MEG. Normally, one photon of light creates one electron of current. With MEG, a single high-energy photon from the sun can kick out 2 or more electrons, dramatically multiplying the electricity generated. This could theoretically push solar cell efficiency as high as 66%, doubling their power output. The impact on medicine could be just as profound. The brilliant, stable glow of quantum dots makes them incredible tools for medical imaging. Traditional fluorescent dyes used in labs fade quickly under light, but quantum dots can shine up to 100 times brighter and for much longer, allowing scientists to track biological processes in real time with stunning clarity. By attaching antibodies to their surface, quantum dots can be programmed to hunt down and stick to specific targets, like cancer cells. A surgeon could use this to see the precise margins of a tumor, ensuring every last cancerous cell is removed. And it goes beyond just seeing the problem. Scientists are developing quantum dots as tiny smart bombs for drug delivery. They can be loaded with chemotherapy drugs and coated with molecules that seek out tumors. This means they can deliver their lethal payload directly to cancer cells, leaving healthy tissue untouched and dramatically reducing the devastating side effects of treatment. Even the light bulb in your home is getting a quantum upgrade. Most white LEDs today use a blue LED to excite a yellow phosphor coating. It works, but the color quality, or CRI, is often a compromise. By adding red quantum dots to the mix, manufacturers can create light that is far more natural and pleasing to the eye, rendering colors more accurately without sacrificing efficiency. This opens the door for human-centric lighting that can change its color temperature throughout the day, mimicking natural sunlight to support our body's internal clock, potentially helping us sleep better and be more productive. Now, despite this incredible promise, there are significant hurdles to overcome on this nanoscale frontier. The biggest one is toxicity. Many of the highest performing quantum dots are made with cadmium, a heavy metal that is toxic to both humans and the environment. For applications like TVs, this isn't a huge risk as the dots are safely sealed away. But for medicine, it's a major concern. The solution lies in 2 paths. First, encapsulating the toxic core in a protective, inert shell like zinc sulfide. The second, and more promising path, is the development of completely cadmium-free quantum dots. Materials like indium phosphide and even carbon-based quantum dots are rapidly catching up in performance and are much safer for biological use and the environment. Another challenge is stability. Quantum dots are divas. They can be sensitive to their environment. Exposure to oxygen, water, and even the light they produce can cause them to degrade over time, losing their unique fluorescent properties. This is a critical problem for a TV or a solar panel that needs to last for decades. Researchers are tackling this by engineering more robust core shell structures and by embedding the dots in protective polymer films to shield them from the elements. Then there's the issue of cost and scale. While making a small batch in a lab is one thing, producing tons of high-quality, uniform quantum dots for the global market is another. The cost of the raw materials and the complexity of the synthesis can be high. The key to making quantum dots commercially competitive for large-scale uses like solar power is to increase the efficiency of the chemical reactions, recycle the solvents used, and move from batch production to automated continuous flow reactors that can churn out material 24/7. Finally, we have to consider the overall environmental footprint. We need to develop greener ways to make quantum dots that use less energy and non-toxic chemicals. And we need a plan for what happens at the end of a product's life. We can't have TVs and solar panels leaching nanomaterials into landfills. This requires creating a circular economy with effective recycling programs to recover these valuable and sometimes hazardous materials. So, from the brilliant screens of our televisions to the front lines of healthcare and the future of clean energy, these tiny crystals are having a massive impact. Quantum dots are a true platform technology, a fundamental tool that gives us unprecedented control over light and energy. The journey from their serendipitous discovery in a piece of colored glass to their Nobel Prize-winning synthesis has been incredible, and the pace of innovation is only accelerating. The challenges of toxicity, stability, and cost are real, but they are being met with equally real solutions. As we continue to unlock the secrets of the quantum realm, one thing is certain: the world of the very, very small is paving the way for a future that is incredibly bright. Thanks for joining us on Fun Facts Online.